Good morning guys. In the last video, we discussed about the bolts that is under tension. And at that point of time, we said the design tensile strength of a bolt in such situation can be given by this formula. And this formula is given in IS 800. Similarly, if there is a prying action that is happening in case of bolt that is under tension, in that case we have to account for an extra amount of force, that is the prying force, that is given by this formula. So whenever there is a prying action, in that case the total force will be T plus Q, and this Q is basically prying force. So we have to calculate this force using this formula, and this is also given in IS 800. Now in some cases our bolt can have tension as well as shear. In that case we have to check this inequality, that it should satisfy this inequality. And this has two terms, one is related to shear, another is related to tension. So this is related to tension and this term is related to shear, and my bolt has to satisfy this inequality for bolt to be safe. Now let us discuss an example to illustrate all this formula that we discussed in the previous video. So let us consider a hanger, that is a T hanger, as shown in the figure. So here we have a T hanger and the end distance of the bolt is 35 mm. So one thing is given, that is the end distance of bolt, that is this to this, that is bolt center line to the end point. This distance is given and this is 35 mm. Two bolts of diameter 30 mm are used to make this connection. So we have two bolts, one bolt is here, another bolt is here, and diameter of each bolt is 30 mm. The end plate is 230 by 150 mm cross mm. So this is the dimension of end plate. So this distance is given. This distance is 230 mm, and the perpendicular distance that will go inside the plane of this figure, that dimension is 150 mm. So if you see, this is the end plate and other dimension will go in this direction. So this dimension is nothing but 150 mm. So this dimension is given. The steel that is used is Fe410 and corresponding yield strength is given, that is 250 MPa. Now the first part of the question says find the tensile capacity of this bolt. So let us focus on the first part and we have to find tensile capacity of this bolt. So to calculate the tensile capacity, we have to look this clause that we also discussed in the previous video, that is 10.3.5. clause number gives the tension capacity, and this can be calculated from this formula. So basically we have to calculate this term as well as this term, and we have to look for the minimum value, that is basically the tensile capacity of this bolt. So let us calculate this. So for plate we have been given Fe410 steel. This means Fu value is 410 MPa. And corresponding Fy is also given, that is 250 MPa. Now for bolt we have 4.6 grade. So bolt of grade 4.6. This means FUB, the ultimate tensile strength of bolt is 400 MPa. That is basically 4 times 100, and corresponding yield strength, that is FYB, that is 400 times 0.6, that is 240 MPa. Now we have been given the bolt diameter, so we can calculate the area of the bolt. So bolt diameter is 30 mm. So this means net area of bolt, that is 78% of the gross area, that is 30 mm in this case. So this is equals to 551 millimeter square. Now we can use the above clause, and that says TDB is equals to TNB divided by gamma MB, and this is clause 10.4.5 as we discussed earlier. Now let us calculate TNB, and that is given in IS code, that is 0.9 times FUB times AN. So now we know each value, and the bolt tensile strength is 400 MPa. So let us multiply by 10 to the power minus 3 to convert the forces into kilonewton, and then the area will remain in millimeter, that is pi by 4 into d square, basically 78% of that. We have already calculated this value, that is 551. So if I calculate all this, we will get 198.48 kilonewton. So this is the value for TNB. So now if you see this clause, basically we have to calculate two terms for TNB. So we have to calculate using this formula as well as this formula, and then we have to find the minimum of these two. So let us find also this one, and then we will consider the second one and the first one, whatever the minimum. So let's call this as a result A. Now let us find force corresponding to the second term. That term is, so we have to consider, let's call this is TNB1 or A, and this is TNBB. So in this case, formula is F by B multiplied by ASB multiplied by gamma MB, and this divided by gamma M0. So we can plug all these values. So this is 240 MPa multiplied by 10 to the power minus 3 to convert into kilonewton, and then ASB is again pi by 4 times 30 square. In this case I don't have to multiply by 78% because this is the gross area, or if you see the code, that ASB is the sank area of the bolt. So we don't have to consider the thread in this case, and that's why we are not multiplying by 78%. That is for net area. And the gamma MB is partial factor of safety 1.25, partial factor safety for material, that is 1.1. So if I plug all this value, this comes out to be 192.78 kilonewton. So I have to find TNB, that is minimum of these two. So minimum of 198.48 kilonewton and 192.78 kilonewton. So this value will be 192.78 kilonewton. Now once I know TNB, we can calculate TDB value. So this TDB is nothing but TNB divided by, that is gamma MB. So this will be 192.78 divided by 1.25. So this value will be 154.22 kilonewton. So this is the design tensile strength for this bolt. So this is tensile strength bolt. that is around 154.22 kilonewton. So we can say the design capacity that is asked in the problem. So capacity of this bolt is equals to 154.22 kilonewton. So this bolt can take a maximum of 154.22 kilonewton if it under tension. So this is the maximum force that it can take. Now let us calculate the second part. So the second part is related to demand. So this says calculate the prying force and the demand for each bolt. Now in actual situation, you see we are applying a force of 100 kilonewton to this bolt, and then basically 200 kilonewton on both bolts. So on each bolt we will have 100 kilonewton of force. That is my T value. So T is equals to 100 kilonewton. This is basically 2T. So T is half of that, that is 100 kilonewton. So we have to calculate demand. So demand for the bolt. So how much demand we have? In this case, demand will come by two sources. One is due to T, another is due to the prying force Q. So the demand will be T plus Q. So in this case, demand is equals to T plus Q. Now let us find Q. We already know T. So to calculate Q, we have to find different geometrical parameters. Now we have to calculate, if I use this formula that is given in the code, and this formula we also discussed in the previous video to calculate the Q force. So in this formula different terms are LV, and this is the distance LV. LE is this distance. So basically in that case I have to consider two terms, and then I have to find minimum of that. So one distance is this, and another distance I have to find using this formula. Beta is a constant, that is 2, eta is another constant, B, E, F naught and T. These terms let us find for the particular problem that is given here. So we can write the formula for Q, and this is equals to LV divided by 2LE and TE minus beta times eta F0 BE T raised to the power 4, and this divided by 27 LE times LV square. Now let us find LV. So basically LV is this distance. So this LV is equals to this distance minus this distance minus this distance and minus this distance. And this distance is nothing but 230 divided by 2. So this distance, if you see, this is 230 divided by 2, and this is 35 mm. And this distance is known, that is this distance divided by 2. So we have been given the dimension of this rod, and that is 16 mm thick. So half of that will be 8 mm. And this dimension is also given, the size of fillet belt is 8 mm. This means this is 8 mm and this is also 8 mm. So we can write LV, this is equals to 230 divided by 2. So this is 230 divided by 2 minus 16 by 2 minus 8 minus 35. So this will be 64 mm. Now the beta is a constant. In this case this value is 2, and LE, that is minimum of end distance. In this case end distance is 35 mm. So this distance is end distance, that is 35 mm. and we have to calculate another term. So this is 35, and another term, that is 1.1 into T multiplied by beta F naught divided by illustress Fy. And F naught is nothing but proof of stress, that is 70% of FUB, that is 0.7 times 400, and all this is given in the code, that is 280 MPa. So we can calculate this term. So that is 1.1, T is 25 mm, and this term will be 2 into 0.7 times 400, and this divided by 250. So Fy for the material is 250. Note that in this case this is Fy for the material, not for the bolt. So this is 41.158 mm. So we have to consider the minimum of these two. So Le is equals to minimum of 35 mm and 41.158 mm. So this is equals to 35 mm. So now I know the value for Le, and we can find value for eta. This is given in the code. This is a constant 1.5, and T is 25 mm, that is given. This distance is T, so this distance in this case is T, and that is 25 mm. Other values we have F naught that we already calculated, and this value is 280 MPa, and Be is the 150 mm, that is the other dimension of the plate that we already showed in the previous video lecture. That is, this dimension is, in this dimension that is perpendicular to the plane, is the dimension that is basically Be, and in this case this value is 150 mm. So if we plug all this, we can calculate Q value. So let us calculate Q. So this is 64 divided by 2 into 35, and the next term is Te. Basically in our case Te is equals to T, that is 100 kilonewton. So this is also equals to Te. So in this case, if you see the formula, this formula says Te, that is basically T, that is half of the applied force. So 200 divided by 2 is equals to 100 kilonewton. So this is 100 kilonewton. This minus 2 into 1.5, and Fy is 280 MPa. Let us convert into kilonewton. So this term now we have in terms of kilonewton per millimeter square. This multiplied by 150, and this is in mm, and then we will have 25 raised to the power 4, that is mm raised to the power 4, and this all divided by 27 into 35 into 64 a square. So this is millimeter square, and this is millimeter. So if you check all these dimensions and calculate the value for Q, this will come 79.8 kilonewton. So this is the prying force that we'll have in this case. Now once I have the prying force, we can calculate the demand, that is the total force. So total demand on bolt, this is equals to T plus Q, and T is 100 and Q be calculated, that is 79.8. So we will have 179.8 kilonewton. So now we have calculated demand as well as capacity for the bolt. So we calculated capacity in the first part, that is 154.22 kilonewton. So this is coming from part A. And we calculated demand, that is the total force that is coming on the bolt, that is 179.8 kilonewton. So this is coming from part B. So you see, my bolt capacity is less and demand is high. So basically bolt is not able to provide the demand. So this means bolt can break. So we can say this bolt is not a safe bolt. So we can say this is basically a case of unsafe bolting. So now question C says, if bolt is unsafe, then how it can be made safe? Only one possibility we have, that somehow if we can reduce the value of Q, then I can reach a situation when we have demand is equals to capacity, or capacity is more than the demand. So my bolt will be safe only if capacity provided by the bolt is greater than equal to the demand, and this can be satisfied only if I reduce my Q value. So I have to reduce Q. So how we can reduce Q? So if you remember the expression for Q, and this expression was LV times 2LE, and this is TE minus beta times eta F naught BEL4 divided by 27 LE LV squares. So this is the expression for Q. So this is basically T. So one solution is we can increase T. So we can increase the T value. So if this term increases, overall this term decreases, then Q value will decrease. Another thing that we can do, that is we can increase LE or LV. So we can increase LV, that case also Q will decrease, or you can increase LE, in that case Q value will also decrease. So let us increase the thickness. We can change all these parameters, but let us say thickness, we can change the thickness of the end plate or flange. So let's check the change the thickness. So we can change the thickness, and the new thickness is 36 mm. Once I have this value, we can again calculate Q. Let's call this as a Q dash 64, and this divided by 2 into 35, 100 minus this all term we have already calculated, and this is 280 10 to the power minus 3 150, and there is only one difference. Now I will have 36 raised to the power 4, and other term will remain same. So this is 36 raised to the power 4. 27 into 35 into 64 whole square. So you can calculate this value for Q. So this is 42 kilonewton. So in this case, now my demand will be 100 plus 42, that is 142 kilonewton, which is lesser than 154 kilonewton. So 154.22. So this value is, so in this case bolt is safe. So you see, in this example basically we discussed how we can calculate the total tensile force in a bolt, And we can also calculate the prying forces and what are the different parameters, how we can calculate those parameters, and what are the significance in the IS 800 code, and then what are the ways by which I can reduce my Q value, that is the prying force, so that my bolt can become a safe bolt in the final. So we can stop here and more we will discuss in the next video.